Here's another way of finding spanning trees. We use a method called the depth-first search algorithm. Now, in general, finding a spanning tree is easy if you have a simple graph. And the idea is to simply eliminate cycles. Any cycles that you see in the graph, you eliminate without losing the connectivity of the graph. So you can delete edges until you get rid of all the cycles in the graph. That is an easy method, but it's only useful for small graphs where you can visualize the entire graph, but it's not robust. Um, we need something that will work for any uh, graph of any size. If you have a graph with 1,000,000 vertices and many edges, the algorithm should be robust and should work for any graph. And we've seen one algorithm that can do that is the breadth first search algorithm, where you start from one vertex and you spread out to all the adjacent vertices. So from one vertex, you find the first level vertices. From the first level vertices, you find the second level vertices. And then you backtrack from each vertex. And as you backtrack, you highlight the edges, and that will give you a spanning tree from that graph. So another way is what we're going to describe in this section. It's the depth first search algorithm. Now the idea here is to label the vertices with consecutive numbers, integers, that will indicate a sequence in which the vertices were found. And here's the key idea, is to go from one vertex and you go as deep as you can within the graph, and then you back up when there's nowhere to go. And then you resume going out as far as you can through another direction. So let's see how this algorithm works. It's very simple. We're going to use this small graph to illustrate the algorithm. You start with a vertex A, and you're going to label it with 1. Now, this number 1 has nothing to do with length of first level vertices or anything like that. You're simply numbering the vertices as you find them. So since this is the first vertex, we're going to label it with 1. And the parentheses also, it will be the same as before. We describe the predecessors in parentheses. Since A is the first vertex, there is no predecessor, so we put a dash or we just leave empty. Now from A, we pick a vertex that is adjacent to A, and it can be any adjacent vertex. It could be B, C, or D. All three are adjacent to A. But again, as I mentioned before, if you have an option, if there is a choice of vertices, let's pick alphabetically. This way, we can compare our answers, and when you do your homework, you should be able all of you to get the same answer. So let's pick the choices that I have is B, C, or D. So let's go to B. Once we get to B, we label it as 2 because this is the second vertex that we encounter. And we label that with 2. Predecessor is A. From B, again, we go to any adjacent vertex to B that is not labeled yet. So adjacent vertices to B would be C, D, and A, but A is already labeled. So from B, we can go either to C or D. Again, there's a choice of 2 vertices here. Let's pick alphabetically. So we're going to pick C. And we're going to label it with 3 and B in parentheses. Now we continue from C. From C, we'll look and we see the adjacent vertex D. And we go there. And then we continue from D. From D, I look and I don't find any adjacent vertex that is not labeled. So that means there's no place I can go from here. So I reach the end of the tunnel here. That means I have to backtrack. From D, I go back to the previous vertex, the predecessor, go back to C. From C, I can continue from there through another adjacent vertex. But all the other adjacent vertices, like A here, is already labeled, so there is nowhere to go from there. Then we backtrack. From B, let's try to go through another route, another direction. Again, there is nowhere to go. That means I backtrack and I go back to A. From A, I try to go through a different direction, and there is nowhere to go. That means I reach the end of the algorithm. There's no place I can go from here. As you can see, the depth first search algorithm, you start with a vertex and you go as far as you can, as deep as you can in the graph until you cannot go anywhere. And then you backtrack, and from that, you go out as far as you can, and then come back, and you backtrack and try to go as far as you can. And eventually, you will have to go back to the original or to the first vertex. And that's how the algorithm works. And what you obtain as you visit each vertex and you label them, you're going to highlight the edge, and that will give you the spanning tree. Here's another example. Let's start with A. From A, labeled 1, and we go to either B or C or D. Again, let's choose alphabetically. Go to B. From B, I can go to either C or D. Let's go to C. Notice that at C, if I try to go anyplace else, I can't. We reach the end. There is nowhere I can go. There is no more adjacent vertices. And then I backtrack to the previous vertex, to the predecessor, B. And from B, I try to go as far as I can through another direction. And so here I can go to B. I can go to D. Go there. And from D, I can try to go out, keep going as far as we can, and there's nowhere to go. So I backtrack to B again. And it's important to backtrack to the predecessor because here the predecessor could have many edges. The degree here could be big. So we have to make sure that we try all the possibilities and we go as far as we can. And when we cannot anymore, then we go back. And that's the spanning tree for that graph.